There are two problems arise with convolution operations. Firstly, every time after convolution operation, the original image size getting shrinks. As we have seen in the above example, 3 by 3 down to 2 by 2. And in image classification tasks, there are multiple convolution layers. So after multiple convolution operation, our original image will get really small, but we don't want the image to shrink every time. The second issue is that when kernel moves over original images, it touches the edge of the image less number of times and touches the middle of the image more number of times. And it overlaps also in the middle. So the corner features of any image or on the edges are not used much in the output. Since we typically use small kernels, for any given convolution, we might only lose a few pixels. But these can add up as we apply many successive convolutional layers. So, in order to solve these two issues, a new concept is introduced. This is called padding. Padding preserves the size of the original image. Typically, we set the values of the extra pixels to 0. In this example, we pad a 3 by 3 input, increasing its size to 5 by 5. The corresponding output then increases to a 4 by 4 matrix. Convolutional neural networks commonly use convolution kernels with odd height and width values, such as 3, 5, or 7. Choosing odd kernel sizes has the benefit that we can preserve the spatial dimensionalities while padding with the same number of rows on top and bottom, and the same numbers of columns on left and right. When the height and width of the convolution kernel are different, we can make the output and input have the same height and width by setting different padding numbers for height and width. When extracting features from the image, we start with the convolution filter at the upper left corner of the input layer, and then slide it over all locations, both down and to the right. In previous examples, we default to sliding one step at a time. However, sometimes, either for computational efficiency or because we wish to downsample, we move our window more than one step at a time, skipping the intermediate locations. We refer to the number of rows and columns traversed per slide as the stride. Stride controls how the filter convolves around the input layer. So far, we have used stride of 1, both for height and width. Sometimes, we may want to use a larger stride. In this example, we show convolution operation with stride of 1 and 2 respectively. We can see that when stride equals 2, the filters move 2 columns to the right-hand side. Normally, programmers will increase the stride if they want the convolution filters to overlap less, and if they want smaller spatial dimensions. To sum up a bit for padding and stride, padding can increase the height and width of the outputs. This is often give the output the same height and width as the input. Stride can reduce the resolution of the output. For example, reducing the height and width of the output to only 50% of the height and width of the input. Padding and stride can be used together to adjust the dimensionalities of the image effectively. While we have described the multiple channels that comprise each image, for instance, color images have the standard RGB channels to indicate the amount of red, green, and blue, and also convolutional layers. When we add channels into the mix, our input and output both become three-dimensional tensors. When the input data contain multiple channels, we need to construct convolutional kernel with the same number of channels as the input data, so that it can perform convolution with the input data. Assuming that the number of channels for the input data is 2, the number of convolutional kernel also needs to be 2. Since the input and convolutional kernel each have 2 channels, we can perform a convolution operation on the 2-dimensional tensor of the input and the 2-dimensional tensor of the convolutional kernel for each channel. Finally, adding up the 2 results together to yield a 2-dimensional tensor. In the most popular neural network, we usually increase the number of filters as we go higher up in the neural network, typically downsampling to trade off spatial resolution for greater channel depth. Intuitively, you could think of filter as responding to some different set of features. The reality is a bit more complicated than the most naive interpretation of this intuition, since representations are not learned independently, but are rather optimized to be jointly useful. So it may not be that a single channel learns an edge detector, but rather than some direction in channel space corresponds to detecting edges. In short, multiple channels can be used to extend the model parameters of the convolutional layer. The higher the number of filters, the higher the number of abstraction that your network is able to extract from image data. Often, as we process images, we want to gradually reduce the spatial resolution of our hidden representations, aggregating information so that the higher up we go in the network, it helps capture essential structural features of the represented image without being trapped by the fine details. Often, our ultimate task will ask some questions about the image. For example, does it contain a cat? So typically, the unit of our final layer should be sensitive to the entire input. By gradually aggregating information, using coarser and coarser maps, we accomplish this goal of ultimately learning a global representation, while keeping all of the advantages of convolutional layers at the intermediate layers of processing. Moreover, when detecting lower-level features, such as edges, we often want our representations to be somewhat invariant to translation. For instance, if we take an image with a sharp delineation between black and white, and shift the whole image by 1 pixel to the right, then the output for the new image might be totally different. The edge we have shifted by 1 pixel. In realities, objects hardly ever occur exactly at the same location. In fact, even with a stationary object, vibration of the camera due to the movement of the shutter might shift everything by a pixel or so. Like convolutional layers, pooling operators consist of a fixed shape window that is sliding over all regions in the input according to its stride. computing a single output for each location traversed by the fixed shape window. However, unlike the convolutional operation of the inputs and kernels in the convolutional layer, the pooling layer contains no parameters. Instead, pooling operators are deterministic, typically calculating either the maximum or the average value of the elements in the pooling window. These operations are called maximum poolings and average pooling, respectively. In both cases, as with the convolution operator, we can think of the pooling window as starting from the upper left of the input tensor and sliding across the input tensor from left to right and top to bottom. At each location, the pooling window hits. It computes the maximum or average value of the input in that particular window, depending on whether max or average pooling is employed. As mentioned, pooling is performed in neural network to reduce variance and computation complexities. We cannot say that a particular pooling method is better over others generally. The choice of pooling operation is made based on the data on hand. Average pooling method smooths out the image, and hence the sharp features may not be identified when this pooling method is used. Max pooling selects the brighter pixels from the image. It is useful when the background of the image is dark, and we are interested in only the lighter pixels of that image. For example, in handwritten digit datasets, the digits are represented in white color, and the background is black. So max pooling is often used. Similarly, minimum pooling is used in the other way around. We already introduced the concept of fully connected layers in the previous artificial neural network session. And these layers form the last few layers in the convolutional neural network. The input to the fully connected layer is the output from the final pooling or convolutional layer, which is flattened and then fed into the fully connected layers. Because the output from the final pooling and convolutional layer is a three-dimensional matrix, to flatten that is to unroll all its value into a vector. This flattened vector is then connected to a few fully connected layers, which are the same as artificial neural networks and perform the same mathematical operations, if you recall. That is linear regression followed by nonlinear activation transformation. After passing through the fully connected layers, the final layer uses either sigmoid or softmax activation function, which is used to get the probabilities of the input being in a particular class. And so finally, we have the probabilities of the object in the image belonging to a particular class.